Hi everyone. In this video we're going to talk about derivatives, and we're going to talk about what a derivative is and what it can help us do, and the sort of questions that a derivative can help us answer. So informally, the definition of a derivative is the function f prime of x that tells us the slope of the tangent line to f of x at any point x. So for example, if I have this blue parabola down here and I want to find the slope of the tangent line at any point of tangency, so in this case right here, well, in order to find that slope, I need to use the derivative of f of x. And so as that point moves about the parabola, the slope of the tangent line is constantly changing. An important thing to note is that the tangent line there is not actually the derivative. Okay, the red dotted line is not the derivative. The red dotted line just has a slope that we found using the derivative. Okay. A more formal definition of a derivative, and there's really two, depending on personal preference, they both do the same thing, but the first is to find f prime of x. We take the limit of f of x plus h minus f of x over h as h goes to 0. And this is something that we've used before to try to find instantaneous rate of change. And because finding the instantaneous rate of change truly is what a derivative means. The second definition we can have that does essentially the same thing is that f prime of x can equal the limit of f of x minus f of a over x minus a as x goes to a. And so if the limit exists, then the derivative f prime exists. And we say that f prime is the derivative of f of x, meaning that the function f of x is differentiable. So differentiable functions have derivatives. And the kind of things that a derivative can tell us, depending on what our original equation or what our original function is measuring, but the slope, the derivative tells us the slope of a line tangent to a curve at any point on the curve. In other words, it tells us the rate at which the slope is changing. Okay, it tells us the instantaneous rate of change. So if I had a function that was measuring height over time, and I wanted to know, well, how is that height changing at any given point? What I'm really finding is the velocity of an object at any time t. So that's one of the most important uses of a derivative. The derivative can also help us find the direction of an object in motion, and it can help us find the rate of change of one variable with respect to another. Anytime that we need to know the instantaneous rate at which one variable is changing with respect to another, that's when we need to use a derivative. So there's several ways that we can symbolize using a derivative. For example, we can say y prime or f prime. And these are nice and they're brief, but they don't necessarily name the independent variable. So let's, for example, let's say we had a function like f of x is equal to 3x squared plus 2x minus 4. I'm not going to go through all the steps to find the derivative, but if we did, we would know that the derivative f prime of x is equal to 6x plus 2. And we could symbolize it just like that. Okay. Another way that we can symbolize a derivative is by saying dy dx, or in other words, a derivative of y with respect to x, or df dx, a derivative of f with respect to x. And again, it really just depends on whether or not your function is in function notation. Is it in f of x form, or is it in y equals form? So if this were in y equals form rather than f of x, we would say that dy dx is equal to 6x plus 2. And these essentially mean the same thing. And we could also write it as df dx, which is also equal to 6x plus 2. These are all ways to write the derivative of f of x. The fourth way that we can symbolize a derivative is to say that d dx, or in other words, the derivative of f at x. And that again would just equal our, oops, I forgot the f of x part. That would just again equal our 6x plus 2. So the d dx of f of x is equal to 6x plus 2. So these are really just all ways. They mean the same thing, they're just ways to symbolize the derivative. So let's say we wanted to use the formal definition of a derivative to find the derivative at a given point. So we're going to start by finding the derivative f prime of x. So in order to do that, we need to take the limit as h approaches 0 of f of x plus h. So that's going to be x plus h squared plus 4 minus f of x, so minus x squared plus 4, all of it over h. Okay. Now, if we're trying to find the derivative at a given point, we have a couple of choices. We can plug in now or we can plug in later. So I'll show you both ways. So let's assume that we decided to plug in right now. So I know that x is going to equal to 2. I'm going to plug that in. So now we're going to take the limit as 2 plus h squared plus 4 minus 2 squared plus 4 over h. H approaches 0. And if I go ahead and simplify, we're going to get the limit as h goes to 0 of 4 plus 4h plus h squared plus 4 minus 2 squared plus 4, that's going to be 8, all of it over h. And if we look closely here, we have a 4, and a negative 8, and those would all cancel out. And so now I have 4h plus h squared divided by h, and we can simplify that by dividing everything by h. So now we have the limit as h goes to 0 of 4 plus h, and as h goes to 0, we get a limit of 4. Okay, so we could say that the derivative of f of x at 2 is equal to 4. Well, the other way we can do it is if we wanted the general derivative function, we don't have to plug in the 2 right away. We can find the overall derivative. So we could say, again, I'm going right back to this step here. I'm just not going to plug in the 2 until much, much later. So if we take this, we're saying that the limit as h goes to 0, and if we simplify x plus h squared, we're going to get x squared plus 2xh plus h squared plus 4 minus x squared plus 4, all of it over h. And again, if we look closely here, we have an x squared and an x squared. Those are going to be subtracted, so those cancel. We have a positive 4 here, and if we distribute the negative, that 4 there would cancel as well. So now what I have is the limit as h goes to 0 of 2xh plus h squared over h. And if we divide out the h, we get the limit as h goes to 0 of 2x plus h. And so now we know that that is equal to 2x. So what we can say now is that f prime of x is equal to 2x. This here is the derivative of f of x. Okay, so now if we wanted to find, okay, let's find the derivative at a given point at x equals 2, we can say let's find f prime of 2, and that's going to equal 2 times 2, which comes out to be 4. Same thing we got earlier. Okay. If we decided to use the other definition of a limit, or a derivative rather, where we take the limit as x goes to a of f of x minus f of a over x minus a, we can see that we're going to get the exact same answer. So in this case here, it's really like a is equal to 2. Okay, so we're going to say the limit of f of x, which is x squared plus 4, minus f of 2, okay, over x minus 2, and we're going to find the limit as x goes to 2. It's going to give us the limit at that particular point. And again, if we wanted to keep it so we weren't finding it just at a particular point, we're finding the overall derivative, we could do the exact same thing here. All right, so instead of putting those in, we could say, all right, we're going to do a squared plus 4, and that's what's going to be subtracted. That's all going to be over x minus a, and we can leave it as the derivative goes to a, or as x goes to a, rather. So again, it doesn't matter whether we plug in now or plug in later. This is the more complicated way, so I'll just leave it this way and let you do the other one on your own. So if we do this out, we're going to distribute that negative right there. And so again, the 4 and the negative 4 are going to cancel. And so what we end up getting is the limit as x goes to a of x squared minus a squared over x minus a. And if we factor that, we're going to get x plus a times x minus a over x minus a, and those will cancel. So now what I have is the limit as x goes to a of x plus a. Okay. So as x goes to a, I'm basically going to get 2a. All right, and since a was 2, we know that the limit there really equaled 4. So again, it doesn't matter which definition you use, it's going to give you the same answer at the same point. Okay. At the end here, let's talk about what it means to have the graph of a derivative. So here we see some function, f of x in blue, and we see the derivative of that function here in red. Now notice that the derivative and the function are not tangent. Okay, they don't have to be tangent. The derivative just gives us the slope of the function at a given point. So if I were to imagine tangent lines being drawn, for example, if I draw a tangent line right there, okay, maybe I should grab a different color here. We can see that that tangent line has a positive slope. So you can see everywhere over here on the graph, we have a positive slope. Let me get rid of that again, and I'll get a better color for us. Let's go with green. All right. So as we see here, all the tangent lines around there would be positive, positive, positive. And then we get right up here towards the top, and we see that, okay, the tangent line right there is going to have actually a 0 slope. It's going to be a horizontal line. Well, we can see that the derivative right there at that point is equal to 0. Okay? And as we draw more tangent lines, okay, we come down around here, right? The derivative here, these would all be negative slopes, negative slopes, negative slopes, negative slopes, right? And you can see down here they're starting to get a little bit less negative. They're starting to even out back to here where, again, we have a derivative of 0. Okay, the derivative there is 0 because they have a horizontal tangent line. So that's why we see here, between here and here, between those points, all of our tangent lines would be negative slopes. Okay, and then we get back to here, we start coming back up, and all these tangent lines are positive. So that's why this area here is a positive slope. So again, if you want to know if the derivative is positive or negative, all you're thinking about is the slope of the tangent going to be positive or negative? Okay. I hope this video helps. Please feel free to come see me with questions.